Natural savorite. Ca3 aluminium silicate 3 volts, Cr. Calcium aluminum silicate. Colored by chromium or vanadium. Often influenced by chromium or vanadium. Natural gemstones. Introduction. Colored stones have a special allure. For centuries, they've been treasured by maharajas, emperors, and kings. They're mined in the mountains, jungles, and deserts of the world, far from the modern world of most jewelry consumers. Locations are often remote, so access can be challenging. Source countries sometimes have complicated laws regarding the mining and marketing of gems. A gem's supply might change from a torrent to a trickle overnight if a country's government changes its regulations and export procedures. Such changes can have dramatic effects on a gem's price, availability, and popularity. Although the big three, ruby, sapphire, and emerald, have the strongest hold on consumer awareness, other enticing gems also compete for attention in today's marketplace. Some, like tanzanite and savorite, were unknown until fairly recently. Others, like spessartine garnet and cultured freshwater pearl, weren't widely available until new sources appeared. What are gems made of? What is a mineral? How do gemologists classify gems? Almost all the colored stones you'll encounter form in the earth. They're inorganic, which means that they're composed of, or arise from, non-living matter. Some other gems, like pearl, coral, amber, and ivory, are produced by living organisms, which means that they're organic. How do chemical composition and crystal structure determine a gem's identity? Whether gems form within the earth or from animals or plants, they're referred to as natural gems. This distinguishes them from materials produced in a factory or laboratory. Gemstones, chemical composition. Chemical composition is like a recipe that describes the types and relative quantities of atoms in a given substance. A material's chemical composition is expressed by a chemical formula that gives two kinds of information. 1. The types of atoms that make up the gem. 2. The relative quantities of those atoms. The chemical formula for corundum, sapphire and ruby, is aluminium oxide, Al equals aluminum, O equals oxygen. This means it's basically made of aluminum and oxygen, and there are 3 oxygen atoms for every 2 aluminum atoms. Quartz is made of silicon and oxygen, with 2 oxygen atoms for every silicon atom, so its chemical formula is silicon oxide, C equals silicon. Diamond has the simplest chemical formula of any gem, C, meaning it's essentially pure carbon. Chemical formula ratio of one element to another. As you can see from the examples above, the numbers in a chemical formula show only the ratio of one element to another. The actual number of atoms in a gem depends on its size. There are many more atoms in a big stone than in a small one. Gem contains few atoms that aren't part of its normal chemical formula. Nothing is absolutely pure, and every gem contains at least a few atoms that aren't part of its normal chemical formula. These trace elements, sometimes called impurity elements, usually take the place of other atoms. Color trace elements: iron, titanium, blue, chromium, red. Color is one of the most obvious effects of a trace element. For example, corundum with very few trace elements is a colorless sapphire. But iron, titanium, or chromium often replace some of corundum's aluminum. When this happens, and the trace elements are iron and titanium, the corundum is blue, a beautiful sapphire. When chromium is present, the corundum is red, which makes it a ruby. Gemstones, crystal structure importance. A mineral's structure, the way the atoms are arranged, is also important. Most gems have an orderly internal arrangement of atoms known as crystal structure. Gems without a crystal structure have no such orderly arrangement. Diamond and graphite crystal structure both are carbon. The difference made by crystal structure is dramatically obvious when you look at diamond and graphite. Both are essentially pure carbon, but they have different crystal structures. Diamond's structure makes it transparent and the hardest known gem. Graphite's structure makes it a great high-temperature lubricant and insulator, but it's soft, black, and opaque, very different in appearance from diamond. Gem species based on its chemical composition and structure. A gem species is based on its chemical composition and structure. For example, members of the gem species corundum, including ruby and sapphire, are made of a combination of aluminum and oxygen atoms. Those atoms arrange themselves in specific ways that give all corundum common qualities. Atoms and crystals structure. All gems, inorganic and organic, are made up of atoms. Atoms are the basic structural units of matter and the smallest units that retain the characteristics of a chemical element. Chemical elements consist of only one kind of atom, and combinations of them make up and color gems. Chromium atoms, for example, color ruby red, and aluminum and oxygen atoms build its crystals. Each gem has its own unique chemical composition combination of atoms. The kinds and relative quantities of atoms that make up a material comprise its chemical composition. Each gem has its own unique chemical composition. Emerald, for example, is a precise combination of beryllium, silicon, aluminum, and oxygen atoms. Atoms and their arrangement within a gem. Unique physical properties. Knowing about the atoms and their arrangement within a gem will help you understand its physical properties, right down to the sharpness of its facets and the perfection of its polish. The types of atoms a gem contains and how they're combined determine everything you see when you look at a gem and how it feels when you handle it. Atoms and crystals structure. Almost all the gems used in jewelry are minerals. Minerals are natural, inorganic substances with characteristic chemical composition and, usually, characteristic structure, too. Synthetic gem materials aren't minerals because they're grown in a laboratory rather than in the earth. 3,000 minerals discovered so far, only 100 qualify as gems. While most gems are minerals, very few minerals qualify as gems. To be a gem, a mineral must be beautiful, durable, and rare. These three factors are what make a gem desirable. Of the more than 3,000 minerals discovered so far, only about 100 qualify as gems. Some gems are rocks, masses of mineral crystals composed of crystals. Some gems are rocks, which means they're made up of masses of mineral crystals. Some rocks, like marble, are composed of crystals of a single mineral, but most contain more than one kind. An example is lapis lazuli, which is made up of the minerals lazulite, calcite, and pyrite. Common minerals. Rocks near Earth's surface, silicates. Many of the most common minerals, the main components of the rocks near the Earth's surface, are silicates, which simply means they contain the elements silicon and oxygen. Most quartz gems are composed almost solely of silicon and oxygen. That's why the term silica is sometimes used to describe quartz. The list of gems that are silicates also includes beryl, garnet, tourmaline, jadeite, spodumene, and opal. Minerals form as crystals. Can be natural or man-made. Minerals almost always form as crystals. A crystal is solid matter with atoms arranged in a regular, repeating, three-dimensional pattern called crystal structure, or crystal lattice. A crystal can be natural or man-made. Gem minerals divided into gem species. Gemologists divide natural gem minerals into gem species. A gem species is a broad gem category based on chemical composition and crystal structure. Mineral species. Beryl. Repeating structure of beryllium, aluminum, oxygen and silicon atoms. The mineral species beryl, for example, is made up of a regular, repeating structure of beryllium, aluminum, oxygen, and silicon atoms. Those atoms, in the proper arrangement and relative quantities, always define that mineral species. But the broad species name isn't enough to describe the wealth of color, glorious greens, blues, pinks, reds, and yellows, of a gem species like beryl. Gem species classify as group. Sometimes several gem species differ only slightly from each other. Because they're so similar, gemologists might classify them as a group. A group is a family of closely related mineral species that share the same crystal structure and basic chemistry, but differ slightly in other details. These differences often lead to differences in physical and optical properties. There are many mineral groups, but only a few contain important gem species. The best-known gem groups are garnet, feldspar, and tourmaline. Almandine, rich in iron pyrope, contains magnesium. The important species in the garnet group, almandine, pyrope, spessartine, grossular, and andradite, share the same crystal structure and basic chemistry, but they have slight differences in chemical composition. For example, almandine is rich in iron, while pyrope contains significant amounts of magnesium. Gem's rarity and beauty. A gem's rarity and beauty affect how it's marketed. These factors also affect its value. They are just as important to understand as things like crystal structure and chemical composition. Gem's rarity, formation conditions, available elements than others. A gem's rarity can be an important part of its value, and that rarity is very closely related to the way it forms within the earth. For example, the formation conditions that produce red garnets are far more common than those that produce ruby. Another factor is that some gems contain more widely available elements than others, so they're more prevalent. How do treatments impact the sales of certain colored stones? A fine ruby can provide the warmth that a diamond's icy beauty can't match. Even so, diamonds are economically more important than colored stones. Gems availability, marketability. Some of the best-selling and most well-known colored stones are blue sapphire, ruby, emerald, cultured pearl, tourmaline, opal, amethyst, and garnet. These gems are more familiar to most consumers than others like zircon and savorit garnet. The difference is due to a combination of factors. One is their availability, in terms of quantities produced. Another factor is their marketability, which often affects, and relies on, consumer preferences. The third factor has to do with treatments and their ethical disclosure, which requires clearly informing consumers about the nature of the gems they're buying. How do treatments impact the sales of certain colored stones? Emerald is an example of the way treatment and public information issues can affect sales. Most emerald rough is fractured by the stresses of formation and mining. As a result, most finished emeralds are treated in some way, usually by filling with oils or resins, to improve their apparent clarity. In the late 1990s, emerald treatments received the attention of the media, and the negative publicity reduced consumer confidence in the gem. High-profile court cases, $143 million import in U.S. 2002 for emerald sales. High-profile court cases and consumer unease about treatments affected emerald sales. In spite of this, gem importers brought about $143 million of cut emeralds into the United States in 2002. And emerald remains the #1 colored stone import into the United States in terms of value. How do treatments impact the sales of certain colored stones? Nomenclature, disclosure, and durability concerns are still an issue in the market today. In the early 2000s, a new type of fracture filling hit the market in the form of high lead content glass in fracture-filled ruby. This material turned corundum with no gem value into material that could be marketed in large volumes. At about the same time, a new type of diffusion treatment for corundum using beryllium entered the market. But it was undisclosed and sold as heat-treated sapphire. This led to a lack of confidence in the sapphire market once the true nature of the treatment was revealed. Treatment gemstones if disclosed ethically. Treatment is just one aspect of the fascinating world of colored stones. And if you approach the topic correctly, it isn't a barrier to sales. Most consumers readily accept gem treatments if they're ethically disclosed and explained in a positive way. Peridot occurs in some meteorites. Cosmic dust contains tiny diamonds. There are some rare gems that are known to occur in only 1 or 2 places. This planet is not the only source of gems. Peridot occurs in some meteorites, and cosmic dust contains very tiny diamonds. Moldavite and tektites are impact glasses formed from terrestrial rocks when meteorites struck Earth. Rarity. Rarity doesn't always make a gem valuable. Pink spinel, for example, is lovely, durable, and rare. Despite its virtues, pink spinel is generally absent from consumer shopping lists. Few people know about it, so there's very little demand for it. Treatment gemstones if disclosed ethically. Demand is unpredictable. Amber, highly treasured in centuries past, is less prized today, although rare specimens can still command high prices. Similarly, jet, an opaque black organic gemstone, was extremely popular in Victorian England but is virtually unheard of in jewelry today. The language of gemstones. Gems are defined and identified according to various characteristics, which are listed for each of the gems. These are some of the essential properties and categories that are used by mineralogists to classify gemstones. Class. The chemical composition and structure of the gem. Some groups of atoms are considered to form the backbone of the crustal structure. Examples include carbon-oxygen groups, carbonates, phosphorus-oxygen groups, phosphates, and several configurations of silicon-oxygen groups, such as chain silicates and cyclosilicates. Crystal system. The basic symmetry of a mineral at the atomic scale, which dictates how it grows. There are 7 crystal systems: isometric, arcubic, tetragonal, hexagonal, trigonal, orthorhombic, monoclinic, and triclinic. A material that is disorganized at the atomic scale, such as natural glass, is termed amorphous. Some gem materials do not have order on the atomic scale, but are organized on larger scales. These include opals, and also organic structures such as shells and pearls. Composition. The atomic content, chemistry, usually described by a mineral formula listing the defining atoms in the mineral and their relative proportions. Refractive index. The atoms in a crystal slow down light, compared to its speed in a vacuum. The refractive index measures this slowing. Since atoms can be more closely packed in some directions than in others, slowing the light more in the denser directions, some minerals have 2 or even 3 refractive indices. Birefringence. The difference between the highest and lowest refractive index in a mineral that has more than one refractive index value. Habit. This refers to the common way a mineral grows, such as in cubes, kidney-like masses, and so on. Dispersion. Each color of the spectrum has its own associated wavelength. The refractive index of a material is different at different wavelengths, so the proper refractive index is measured at 589 nanometers, in the yellow region of the spectrum. Dispersion measures the difference in refractive index, for light traveling in the same direction, between blue-violet light, at 486 nanometers, and red light, at 656 nanometers. Specific gravity. Specific gravity measures how much an object weighs relative to the same volume of water. A gem with a high specific gravity, such as white jadeite, will feel heavier in the hand than one with a low specific gravity, such as white opal. Hardness. This is the resistance of a material to scratching. A harder mineral scratches a softer mineral. Hardness is measured using the Mohs scale, according to which talc has a hardness of 1, gypsum 2, calcite 3, fluorite 4, apatite 5, orthoclase 6, quartz 7, topaz 8, corundum 9, and diamond 10. Cleavage. This is the natural tendency of a mineral to break along flat planes. These breakage surfaces correspond to planes where the bonding between atoms is weak. Fracture. This is the way a mineral breaks along lines other than a flat cleavage plane. A fracture may be described as, for example, conchoidal, curved, or shell-like, hackly, jagged, splintery, or uneven. Luster. This is the way that a mineral reflects light. Transparent minerals can have a luster that is adamantine, diamond-like, vitreous, glassy, resinous, like amber or plastic, silky, dull, earthy, or pearly. Opaque minerals may also have metallic or submetallic, almost metallic, luster. Further testing. There is more to know about a natural gem than just its species. One might want to establish its exact variety first. Is it a ruby or a pink sapphire? Second, does the gemstone contain independent evidence as to where it was formed, or where it was found? Third, can one be certain that it is natural rather than synthetic? Questions such as these have a bearing on the importance and value of a gem, and often the answers can only be provided by techniques that are beyond the means or the technical know-how of most collectors. UV visible near IR spectrometry looks at the wavelengths that a gemstone absorbs. This can be used to determine whether certain colors in gem are naturally occurring, or owe their color to treatment with ionizing radiation. Among those techniques are the several varieties of spectrometry, which is measuring the ways that gemstone affect the various properties of light at the molecular level. Infrared, IR, spectrometry. It's a different means of measuring light. It is sensitive to the presence of plastic and polymers in gemstones. This makes it very useful for establishing whether surface-reaching fissures in a gem have been filled with artificial materials. IR spectrometry also shows in the presence of water, which means that it can be used to distinguishing some synthetic gems from their natural counterparts, because the natural gems tend to contain tiny quantities of water, whereas these synthetics are anhydrous, that is, dry. Raman spectrometry can target mineral inclusions in gemstones and identify them by the characteristic spectral patterns of the light that they emit. Inclusions can serve to verify that a gemstone is natural rather than synthetic. More than that, they can act like a geographical fingerprint, pinpointing the location where the gemstone was mined. X-ray fluorescence, XRF. Technique that exploits a different part of the invisible spectrum. It can be used to identify the elements that are present in a gemstone and, under the right circumstances, to measure the exact quantities of those elements and so determine the gem's mineral formula. The presence or absence of certain elements is yet another way of determining whether a gem is synthetic, or if it has undergone a treatment. X-raying can highlight the internal structure of pearls, for example, and so distinguish natural pearls from cultured ones. Some pearls emit luminescence when subjected to X-rays, which can be used to distinguish freshwater specimens from saltwater ones. Photoluminescence testing. Practically the only way to detect high-pressure high-temperature, HPHT, a treatment that can render brown diamonds colorless. Using laser induces breakdown spectroscopy, LIBS, or an ion microprobe are ways to detect a sapphire that has been turned from pink to orange by beryllium diffusion. Importance of International Gem Testing Lab Report. All these methods of testing add up to a fine mineralogical armory, a battery of sophisticated technology that can be found only in a gem testing laboratory. And you can be rest assured that the gemstone is 100% natural. Gemstones key concepts. Most gems are minerals. To be a gem, a mineral must be beautiful, durable, and rare. Changes that take place in a gem's source country can drastically affect its availability and price. Treatments improve the marketability and availability of many gems. Most consumers accept gem treatments if they're ethically disclosed and explained in a positive way. In spite of treatment that's sometimes extensive, emerald is the #1 colored stone by value imported into the U.S.